So, you can see that I put the schedule over there. Sorry, I don't have the kids poster, but the schedule is 77, 78, 79. And test is Thursday. Test 3 is Thursday. It's through last week's material. So that gives you a good 3 days to master even most new material, and hopefully it will go well. 70. So the test is through 76. 76 is odd powers of trig, like this one on tonight's homework. 75 is continuity, which you guys are pretty good at. 74 is force, and like this. So, towards practicing the newer material, would you go to your homework before we start hitting the notes? Let's warm up a little. And do 5 on the homework, please. I often do a warm-up off the homework just to review a recent idea. And then get off the homework. So what we call the basic principle. Use your notes or ask a buddy. Thank you. We're doing these two off the homework as a warm-up before we get to the notes. Yes. Are we ready for 5 rather? The antiderivative is?
Sine cubed x over 3.
Sine cubed x over 3. I agree.
Minus sine x
Plus C. All right, that's an odd power trig problem. What do you think? Easy enough?
Yeah.
Okay. Try the force problem number 3. And let's see how that goes.
What is the dash?
What is what?
Like what's that has no meaning.
Oh, yeah, you're right. I don't know why the dash is better. 10 by 10 by 10. Good point.
Well, you usually are. It's much like
You said you require a picture for all of these.
I require that you show me when the origin is. Yes. Otherwise, I have no way of verifying you said it.
It's 4,900,000.
So the picture doesn't have to be beautiful, but it does have to locate the axis or the origin. On these, I definitely don't mind if you integrate with your calculator, although usually the integrals are really straightforward. You may use your calculator to evaluate the integral on these problems. ¿Listos? ¿Sí estamos listos o no estamos listos? Estamos listos. Speaking, when you speak French, how do you say, are you ready to French?
Oh, I thought you were saying, are you finished? I was like,
No. Tu as fini?
Finny.
Fini? Tu as fini?
You have finished?
You
Yes.
have finished? Tu as fini? Oui. Oui. All right. So say it's relative, but I am going to put the origin at the lower left corner of the container. You follow? Oui. So 10 there, 10 there. Force depends on the weight density, the distance, the depth rather, excuse me, the depth of each slice and the area of each slice. Right? PDA. Yeah. Yes, that is how indeed I remember it. Force is, PDA is very important. All right? So, or requires force on my part. All right, so 9,800, what is the depth of each slice? 10 minus y. What is the area of each slice? 10 wide and dy high. So I agree. What is the limits of integration? 0 to 10. All right. So it sounds like you're doing okay there. Whatever the units are, the units, your answer is force, so the units are newtons. Okay. Moving on to today's lesson then. Today, usually this lesson would be in the same chapter as that lesson, that force lesson. Kind of a physics applications of integration chapter. Okie dokie. So let's see. Did I push record on this? Yeah. Okay. So check this out. Say I was pumping fluid out of a container by a straw or whatever a pump's attached to it. So, yeah, a couple of years ago I actually had I did used to do fun stuff, but it takes so long to do fun stuff, and then I don't have time to practice, so I don't do fun stuff anymore, sorry. But the fun stuff I used to do was I had 4 students up here and competing in a who can empty their glass the first competition. The first student had just a normal glass of water and a normal sized straw. The next one had 6 straws together, and the glass was practically on the floor, and he had to empty his glass, or she did, I can't remember. The next one, it wasn't actually mud. I got a Frosty, and they had to empty the Frosty with the straw. Okay, and then another one was just this huge tub, and they had to empty theirs. The idea was it was meant to communicate the variables at work and how much work it takes to empty a container or to pump fluids out of a container. So what does it look like based on that? The variables are that affect how much work it takes to empty. Distance obviously has an effect. Because work is force applied or force it takes to move something over a distance, then the greater the distance, the greater the force. So distance definitely matters. The further you have to pump the fluid, the more work. What else? Density. The weight density of the fluid, think trying to suck a Frosty out of the straw. And more than area is volume. Now normally on a force problem, I don't care if it's this or this, the force on this face would be the same. But for work, it's not about area so much as volume. And volume, this distance starts to matter. All right, so because it makes for more volume, more work. In terms of math relationships, you have direct and inverse variation. You remember that in algebra 2? Direct and inverse variation? Mm-hmm. Give me 2 variables that relate directly. We talk rates, okay? You would say there's a direct relationship between
Hours studying and exam scores.
hours studying and exam scores. Those are directly related because I assume the more hours you spend, the higher your grade. That's a direct relationship. Give me 2 variables that are inversely related. Think dividing something up into groups.
You just did that last.
What?
It's a massive separation.
They have a negative or an inverse relationship?
Yeah.
Okay, awesome. I was thinking something like, if I have 100 people and I want to divide $100 and I want to divide it among people, then the more people, the less each one gets. That's an inverse relationship. In this case, are these variables relating directly to work or inversely? The more distance, the more work?
Yes.
Yes, that's a direct relationship. The more density, the more work.
Yes.
That also is direct. The more volume, the more work.
Yes.
In all cases, direct. And so work depends directly on, there's some constant in there, I suppose, but distance, density, and volume. It's the direct product of all those. Now, why this then is a calculus problem is think height or distance. This slice, when I say I need to pump this slice up and out of the container, it's going to take a different amount of work than it takes to pump this slice down here. Why? They have the same volume, they have the same weight density. The distance you have to pump each layer is going to vary. And so even by just slightly changing microscopically, you're talking about a different distance. And so that's what it requires a calculus approach to it. So here we go. You have a rectangular prism with base 8 by 6. And the height is 10 centimeters. And it's filled with water. Oh, golly gee. It just occurred to me in that last class they didn't care about the units. They just said, hey, here I go. All right. It's half filled with water. And you're pumping the fluid out of the container and over the top edge. There's a little hole in the top of the container that you are pumping out and over. It'll usually say that. I forgot to type that in. All right? So we're trying to empty the container. Imagine if you like there's a straw or whatever. It doesn't actually matter if that straw rests on top or bottom. It'll always come out the same. Okay, let's first draw and locate axis. Draw, locate the origin. Where do you want to put the origin? At the top of the container, the top of the fluid, or the bottom of the fluid? Bottom of the fluid. Sounds good. Okay, so I'm going to do that. And I'm going to draw in the important things. Now, normally, on force problems, this guy part coming back here, this doesn't usually matter, but on these problems it will. That said, I sometimes leave this out because if it makes your picture too congested, that's fine. I don't care if you draw that in. Just keep in mind you have to consider it, right? Okay, I located the origin. Check. I would start by write the big idea. The more you write this, every time you write it, it gets into your brain a little more, and that is the work depends on the weight density, the distance, and the volume. The more you write it, the more you remember it. All right? Find each element. The weight density is given. They say it is water. So the weight density is 9,800. The limits of integration. Where are they? 0 to 5. I only care about how much work is done pumping the fluid. Well, there's only fluid from 0 to 5 because it's half filled. The distance. This slice here, do you agree there's a slice of water at 1 meter, or maybe the units are already a problem. Anybody seen a problem with the units? Yeah, this is 9,800 newtons per cubic meter, and this is centimeters, so we're going to have to convert that to meters, and wouldn't it be 0.05? You want to do it then? All right. You with me? Okay, what about the distance? Say there's a slice at 1, right? How far does that have to be pumped? What distance must I take that?
10 miles wide. 10 miles.
To get it to the top, I'd have to take it
10 miles.
9 centimeters, right? Do you agree?
Yes.
Okay, so generally speaking, if I have a slice that's varying at y, then to get it to the top, I have to pump it 10 minus y in distance. Now that's one difference already between force and work.
Wait.
I don't care about getting it just to the surface like I do at depth. I'm trying to take that slice all the way to the top and out. So it's about the top of the container, not about the surface. Yes?
That would be 21 then?
Yes, sorry. That's probably what you were, is that what you were going to say, Andy?
Yeah.
Okay, sorry. Yes, point 1, you're correct. Thank you. Yes. So point 1, and maybe I should have called these 0.05 and point 1 right away so I can make that down there. All right, now the volume. That's the volume, not of the whole container. Remember, that's the volume of this little slice. I'm just moving that one slice and then this slice and adding all the work I require to take all those sheets out. What's the volume of that sheet? 0.08 in width, 0.06 in length, I guess you could call it, and the height? dy. And crank that out. And what about the units? Now, the weight density is newtons per cubic meter, yeah? What are the units on the distance? Meters. What are the distance on the width?
Meters.
Distance on the length?
Meters.
And the dy? Meters. So, meters cancel, and you're left with Newton meters, which is joules. The amount of work will be in joules. And in the Saxon book, they don't give you mixtures of feet and all that nonsense. It's just, they just do newtons and meters, and so it'll always be joules. Are we cool? And if you need to, you can punch that in your calculator and you'd be wrong. Questions on that first? Okay. So we get slightly more complicated than here. We're pumping this, I guess you could say it's a semicircular barrel, up and out. I know it doesn't look circular, it looks more stretched and elliptical, but it's circular. I mean, I just got funny looking buttons and it's stretched. My bad. All right. In terms of where to put the axis, if you have a circle, I beg you, don't put the origin at the bottom because then the equation is hideous. It's x squared plus y like it's terrible, terrible. No, instead, put the origin at the center of the circle. I won't mark you off if you do it the hard way and you do it well, but golly, in terms of making your life easier, it's so much easier if you have a circle if you put the origin at the center. So, I'm going to put the origin at the center, and I'm going to call this, I'm going to do this better because that's close. It's only a half circle, and the radius is 4, and so the horizontal will go from 4 to -4, right? And the vertical goes down to a low of -4. And I tell you what, in order to make this problem more interesting, let's change this to a height of 1 meter. Would you change that to 1 meter for the height of the fluid? It's 1 meter high here, depth, whatever you want to call it. All right, so if I want to call the water surface here, and it's 1 meter high, then that would put it at a y of -3. Okay? Notice these are meters, not centimeters this time. Are we good so far? All right, so work is rho, distance, volume. What matters is how deep, how dense the fluid is, the distance you have to pump the slices, and how much volume. In this case, because the fluid is given to have an 8,000 Newton per cubic meter weight density, I'm going to put that there. The distance. There's a small hole at the top of the container. And remember, it's a semicircle, so it's not a full circle. So what's the distance you must pump each slice? 0 minus y, yeah. The top is, because I put the origin at the top of the container, the top would be at level 0, and the bottom is y. So upper minus lower is 0 minus y. The volume. Now, again, it feels like I should be doing something with the circle, but imagine if you took a super powerful slicer and sliced it right here and looked at the cross section. If you looked at the cross section, would it be circular in nature, or would it look just like a rectangular sheet? Yeah, so it's a rectangle. It is still a volume of a rectangular prism. So think length, width, and height. It won't always be that case, but in this case it is. The volume of each sheet or slice is length, width, and height. The width. What's the width of each? Constant or variable? Variable. X or 2x? 2x. Okay, so that's actually width. I just switched that. What about the length? 12. And the height? dy. All right, I'll come to that x in a second, but let's go back to the limits of integration. What are they? -4 to -3. All right. Now, we're in good shape, but just like those previous problems in force, if we get a varying width, then we need to replace x with some y-ish fact. What's an x-y relationship? This is where the circle benefits us to have it at the origin. X squared plus y squared equals 16, so x is? Square root of 16 minus y squared. Go over here, and moved over there. 2, and in place of x goes 16 minus y squared times 12 dy. And then again, if we wanted to put that in our calculator, I suppose you can move all those two constants out front. That's the idea. If you had to integrate that by hand, you move the constants, you might have a little bit of a u sub case in there, right? You agree? Okay. All right, that's the big idea. Now, by far the biggest problem is, now that you have two different kinds of problems, you get the two confused. So let's be clear on the differences between the two, work versus force. Say you had a problem like this, it wouldn't matter. In force, it's rho dA. Rho is the same. The D, though, here stands for what? Displacement, depth, distance? Depth. Remember, force is about how deep. There's more pressure at the bottom of the container. So depth. Depth, then, when I say depth, is that starting at the top of the fluid or the top of the container? If I have a container that is 5,000 meters tall and the water level is at 50, then how deep is this slice? 50 minus y. So is it about the top of the container or the top of the fluid? Fluid. Okay. It's top of the fluid minus y. And the area is the area of each slice, not the area of the container. Area of a slice. The limits of integration, are they from the fluid low to the fluid high, or the container low to container high? Is it about, do I need to calculate the force up here where there's air? No, I want force down here. So is it about fluid or container? Fluid. Fluid low to fluid high. Now, if you compare that to work, work is rho dV or PdV, which I don't know what that whatever that stands for. Never mind. The D, this D stands though for not depth, but distance. Distance, when I have to pump a distance, is that about the top of the fluid or the top of the container itself? All right, so here the distance is top of the container minus Y. And V obviously stands for the volume of a slice. Rather than the area, we talk about 3 dimensions. All right, and it's still, I don't want to pump where there's fluid, so it's still fluid low to fluid high. The limits of integration for both are all about fluid. Let's do a little one of each, which will happen, and the first time it's on a test, people tend to blow these and get the 2 components mixed up. So you've got this rectangular trough, or triangular trough. Top edge 3, side 4, height 7. I'll explain what I mean by those in a second. Filled half the way up with gasoline. Find the force in A and the work in B. I don't like when the container goes that way, so if you don't mind, I'm going to draw it this way. Where do you want to put your origin? You definitely have to define your origin. Bottom is good, because that'll be the easiest to write. Now when I say top edge of 3, that's here. Side of 4 meters, that's here. The height of 7 meters. I'm not talking layman's kind of height, how tall is it, like a person on the street would call. Height in prisms is the distance between the 2 bases. I don't care what's going up or down. That's a non-issue. I could rotate this any which way, and the height's still the same. Height is the distance between the bases, so the height is there. Right? Right. Okay. Try A with a Math Amigo or on your own, and let's compare how much force on the face. Keep in mind that it's filled half the way up. Yes. What are your limits of integration? What's the depth? 4 minus y or 2 minus y? 2 minus y, because you're talking depth relative to the surface of the fluid. The area, constant width or varying width? X wide or 2x wide? 1x wide, dy high. What's the relationship between the variables? What's the equation? Okay. So in terms of this line before I solve for x, what's the rise and run? 4/3. Solve for x, then in terms of y, x is 3/4 y. So your setup, if you did this properly, with the same origin location, should be something like this. Do we all agree? Okay, try B. Try the work problem of today. See if you're getting the work. Okay? Weight density is the same. The limits, do they change for these problems? No, it's still about 0 to 2 where the fluid is. What's the distance that you're pumping each slice? 4 minus y now, because you have to pump it to the top of the container, not the surface of the fluid. The volume, how is it play off of the previous area? It's just like the area, but times 7, yeah. So it's got that same 3/4 y for the width, 7 for the length, and dy for the height. All right, so there's a lot of overlap, but not identical. All right, now a challenge problem. For those of you who think this is ridiculously easy, here's a good challenge. Try this, talk it over with your math amigos, and we'll go over in a minute. That's where I put my origin. It's up to you. Requires you to gas and improvise. It's not just regurgitate.
Since it's like there's the top of the
How'd you find your area? That's a good idea. It comes on this one. Because it's not the area to start.
How do you see this?
So you're talking about the area that's applied to the outside, so that's more applied to the perimeter. What's the geometric figure you're applying area to then? It's more of applying the area to this guy on all its bases, so if you were to unwrap it,
Oh, so yeah, it's
Just the area of this, like, so it'd be dy. Yeah, yeah. So 0 to 1.
so the width of that is the circumference.
So that's
So your force integral is 9800, 0 to 1, depth, 1 minus y, area of the slice. 2 pi, oh, pi d, you're doing pi d, that makes sense. Or whatever. 2 pi r, and the r is 0.4, so I see where you're saying 0.8, I agree. And the height? Y, nicely done, yes. Did you do the work or give you another minute? That was an or question. Yes.
Yes.
It's still an or question. Which one is? Yes, give you a minute, or no, you're ready.
No, ready.
No, ready. Minute. All right. I heard somebody say a minute, so I'll give you one more minute.
Yes. I did.
Yes.
Wait, so the slice would be.
Why will the slice of the meat?
That's the question.
That's the question. What's with meat? I got a question. What's the shape of the slice? Not a rectangle. This is a disc. It's the volume of this disc.
Oh, wait.
Okay, so it's the volume of a small, tiny paper thin cylinder.
Oh. So would you just.
So 9,800 is still the constant. It's still 0 to 1 because that's where the fluid is. The distance? 1 minus y. Generalize. These will be the same in the cases where what happens?
It's all the way.
It's all the way full. Yeah. So what about then the volume? Pi 0.4 squared for pi r squared. Height? You got it. Excellent, excellent. All right, that's it. Questions on set 73, 4? I don't know. 73. All right, the keys. I have the keys to 73, 74, and the extra practice online. I will also put the keys to 75 and 76 online because we need to start getting a little caught up. So hopefully those will get you started if you get hung up. 73 questions if you have one. Give me 73 questions. And on 73. We did?
We didn't finish it out.
We didn't finish 10. They said.
Yeah, we did it.
Almost
It was the absolute value. It doesn't matter.
Oh. 23, I don't have it.
24. 24.
Oh, okay. 10 is just to ignore the absolute value, basically, because it's positive anyway. So that should be good. You can just blow off the opposite value. 24 and 25. 24. I don't have much. Okay, so you've got this cubic x cubed plus ax squared plus bx plus c. And I suppose you're supposed to fill in the gaps, a, b, and c. You have an inflection point at 0, -2. You have a relative min at -1, 0. I guess the first thing I can do to help you get over the hump is to understand that each of those really communicates two conditions. For example, inflection point, first and foremost, because it's a point on the curve, I can operate in f and say -2 equals 0 cubed plus 0 plus 0 plus c. So just the fact that they're giving me a point, the y-intercept, tells me c. And also, inflection point for a polynomial is because the second derivative equals 0 and changes sign. It's not always necessarily the case that it equals 0, but for a polynomial it is. So that tells me that if the derivative is 3x squared plus 2ax plus b, and the second derivative is 6x plus 2a, then the second derivative at 0 is 0. If I look at the second derivative and say it's 0 when x is 0, that implies that a is 0. What are you, oh, you're looking at that over there? Oh, no, that's not an inflection. That's not a point on the second derivative. That's a point on the curve. Okay. When you go to use that, it implies the second derivative is 0 when x is 0. Yes?
We can't write that the inflection point is your double
That is only true for that's true for polynomials, but not for every function. Okay, so I'm only using that here because it's a polynomial upward. There's a lot of things that, for example, this, it has an inflection. No, it doesn't have an inflection. The second derivative will change, or it will equal 0 at, actually, let's go x to the 4th. No, I'm trying to find the point. There's a lot of places where the second derivative fails to exist. Actually, it's like this. And it changes sign for inflection point. So I don't want you to fall into the trap of thinking it's always the case that it's just the second derivative is 0 for polynomials. Okay? All right, so at this point, I have a lot filled in. I already know that f of x now is x cubed plus bx minus 2. Just from that one inflection point fact. I could also use the relative min fact. That could be used in two ways. It could be used as a point on the curve, which is to say 0 when x is -1. And I don't even need to get to the derivative thing it talks about. That's enough to find b and call it good. I don't even need to get into the derivative as 0 on a polynomial out of x or min. So, that should get you going. 25. This isn't placed, is it? You've got a function minus 3x squared plus 2. I assume the part 1 was A was fine. You were able to get an tangent line equation here? Okay. Whatever the point was. B was B hard. Find the coordinate of the x-coordinate of each point where the line tangent to f is parallel to y equals -2x plus 4. Parallel, if the tangent is parallel to y equals -2x plus 4, what does that imply about the derivative? The tangent slope comes from the derivative. And parallel means same slope as that one. Well, what slope does that have? -2. So you are solving for the derivative, which is 4x cubed minus 6x equals -2. That involves some cubic skills on your part. Yay! Actually, I didn't use any cubic skills. I just used guess and check. I just said, hey, looky there, x is 1. But if you were to synthetically divide, I think you'll see 1 is a point where this is true. But a cube could have 3 solutions, so it could be the case that there are 3 places where this has the same slope. So if I go on, I get that x equals 1 works, which is to say x minus 1 factors out. And if I take x minus 1 out of the cube, then what's left is this depressed equation. What's the powers of this equation? 4x squared plus 4x minus 2. So the derivative solutions have to be solutions to this. I know x equals 1. This one you can now solve by quadratic formula for the other 2 points. You should have 3 points altogether. And that's good. Okay. Any other questions on 73? All right. Maybe I could get one question on 74. 7. Let's just leave it at that because that's probably all I'm going to get to. 74, number 7. That's not changed at all, right? It's derivative. So it's changed. Okay. Find the O. I didn't have a calculator to find it down here. That's all right. We'll get it set up and you can calculate. So you have y equals negative x squared plus 6x minus 4. And the x-axis. And then you're going to revolve that region around the x-axis to find the volume. I didn't say, but I am okay if you use a calculator to find the zeros. If you look at this graph, let's see. X squared 6x minus 4 plus 9 plus 9. I don't know how good your completing the squares skills are, but I have mad completing the square skills. This is a parabola shifted right 3, up 5, and opening down with a y-intercept of negative 4. All right, pretty cool? With that, I could also see that this would cross the x-axis at negative 5, square root of 5, plus or minus the square root of 5. The asymptotes, or sorry, the x-intercepts are going to be 3 plus or minus root 5. Am I going too fast? Are you kind of seeing where I'm coming from? Sort of. 3 plus root 5. All right. This then is rotated about the x-axis to create a volume of revolution, making many disks. I'll be interested in seeing how this goes on the test. How are you doing on volume by disk? Good. Okay. The idea being that the volume is the sum of many cylinders. So it's many pi r squared h's. Pi is fine. What's the radius in this problem? The function, okay, so the radius squared is the function squared, negative x squared plus 6x minus 4, and the height of each cylinder is barely this much. Is it barely dx or barely dy? Dx. And the limits of integration are negative positive. All right, that is not quite enough to get 74 turned in, but 73 is due today. Have a nice day.